We'll be continuing in this packet, and this is worksheet 1.1, measuring reaction rates. Let me get back up to where we're going to be working. I'm going to be starting on problem number 3. There's problem number 3. When butane is burned in air, our first order of business is to write a balanced chemical equation. I'm going to go a little thinner here. I don't have a backup on here. C4H10. This is the chemical formula for butane. Is burned in air, which is 13 O2. I should light. I'm not going to tell you the 13 yet. Ignore that. Yields CO2 plus H2O. Our balanced chemical equation, this is one of the things you have to be able to do. So we're going to have a balanced chemical equation. You should stop now and balance this. Once you have it balanced, you can get this turned back on. So I'm assuming you have it balanced and you now turn this back on and you got the following coefficients. We're told that butane is consumed at a rate of 0.116 grams of butane per second. We are asked to determine the rate of production of CO2. So we're going to do here, and I'm only going to do my molar masses to 1 decimal place today because it just would take me a little less time. You can do this to 2 decimal places, which would be smart. This is a stoichiometric conversion, so I'm going to go grams to moles. I don't have a backup key here. I'm used to having a little backup key here. And then I'm going to use the molar mass of carbon dioxide, which I'll go to 44.0. Again, you could go to 2 sig figs or 2 decimal places there. And this should be CO2. I don't know what I was thinking about here. This is my mole. Gosh, I'm having a very hard time getting this on here. Now I can do my mole ratio. And I can see I have an 8 and a 2. And then I'll have my 44.0 grams of CO2 per mole of CO2. My moles of CO2 cancel, my moles of butane cancel, and my grams of butane cancel, giving me grams of CO2 per second. You can punch this number in. You're going to report your answer to 3 significant figures. Check your answer key because I'm out of room. Your units will be grams of CO2 per second. Next, we're asked, let's see here, 2. What would be a good way to monitor the rate? Oh, I've got a new equation here. This is number 4. So here's a next equation. And you'll notice that I have 2 colorless species turning into a colorless and a brown species. So what would be a good way to monitor the rate of this reaction? And a good way to monitor this reaction that would be the color, the intensity or change in color divided by the change in time. And why wouldn't pressure be a good way to monitor the rate of this reaction. And it would not be a good way because the total moles of reactants that are represented, which would be 1 and 1, a total of 2, equals the total moles of products, which is 2. 1 and 1. Okay, what's next? I don't want to do 5. Okay, let's do this one. So here we've got a graph of hydrochloric acid on the y-axis and time on the x. And we are asked to draw the shape of the curve we would expect if we plotted HCl versus time. You can see that HCl is a reactant, so it's being consumed. It's going to start at a very high. Now, we're going to be using it up, and it's going to get used up, and the change is going to continue to get less and less and less as time goes on. As our concentration of HCl decreases, the rate at which it is consumed also decreases because its concentration is less. The very highest concentration we have is right here. Oh, that's not really working. It's like I wanted to. And when we get to right about here, we've used a lot of it. We've used up lots of HCl, which means it's no longer as concentrated. When it's not as concentrated, we'll have fewer successful collisions. And the reaction rates will slow way down. Here's an interesting question, and you could stop and discuss this and then come back if you wanted to. Some examples where we might have wanted to increase and then to decrease the rate of a particular reaction. And here's just a few, and these are on my key. Burning of fuels for high performance. Setting of glue, curing paints, we want paints to dry fast, explosives, cleaners, disinfectants, we want all those things to work quickly. And when we want to decrease it, we might want to decrease fire when it's unwanted. How about aging? I would like to slow down the aging process. We'd like to slow down the corrosion process, like rusting is an example of corrosion. Those would be some good ones. And then we're going to talk about 2 reasons why water is effective at putting out fires. H2O coats or covers the fuel. So the O2 and fuel can't come in contact and can't react. And the other thing is, number 2, it cools. So there's 1 and there's 2. Okay, what's next here? Whoops. Number 12, I'm going to look at number 12 and just tell you a couple things. You're going to calculate the reaction rate here using change in mass divided by change in time. And this is going to be the same, just at a different interval. And then think about this question. Check my key. This you can do and check. This you can do and check. And this you can do and check. And you're going to be answering all of these based on this. You can use examples. Let me see my next one. And all the answers for that one are on the answer key, which is available. Just don't like walk out of my room with it. I'm pretty sure I've got them online too. Next, I'm going to check what's 13? Ooh, got some bleach there. So this one is another one that you can do. This is sort of a fun one. So you can do all these and check on the key. You don't need me to do that either. And this one you can also do. This one is just an interpreting graph. This one's easy. So you can do this and check on the key. Because this is the first thing I'd like you to do today. So you will have watched part of this. You'll have this shut off for part of this. This all together should take right around 20 to 25 minutes. And that's enough time if you stay on task. Make sure you're staying on task and doing what you need.